Okay, so this will be the final video where I teach or basically explain the difference between the median and the mean. I mean, my last video did it pretty well, but I thought I'd ended up or finish it off with a last video because I'm honestly getting tired of this topic. But as we know, when you have random variables or a distribution that has significant outliers, right? And when I say significant, I mean extreme outliers often. Right, the mean is going to be pushed away from the actual central tendency of the data. It won't represent a typical data point anymore. It'll represent the whole of the data. Whereas the mean, assuming that you don't have a bimodal distribution, will be more representative of the average point. Assuming that your underlying distribution is normally distributed, or roughly normally distributed. Okay. Here we're simulating 10 seconds of EEG data, sampled at 100 cycles per second, or hertz. And we have 1,000 points. And we add a bit of sensor artifacts in here, which create, again, those outlier values. Here we're adding 4 of them. And we have our true signal based around 80 millivolts, because EEGs measure electrical activity of the brain. So we have 80 millivolts, the person's in deep sleep, and these random artifacts that come in. Well, we get the central tendency values, and we see that the mean is around 87, which is not accurate for the average value, whereas the median is 80.14, which is pretty much exactly what our Y translation is. And when you factor in the fact that it's a sinusoidal function, right, that has the same amount of Y, positive and negative Y translation per cycle, then basically this ends up canceling itself out, and the only thing you're left with for the average data point is this random noise that's normally distributed between around 0, and because it's around 0, you have -5, +5, +10, but it ends up basically canceling itself out as well, because normal distribution around 0 with the standard deviation of 5. Again, you'll have the positive and negative values. So it's actually like perfectly representative, almost perfectly representative of the actual signal that we get, the typical data point. Whereas the mean is 86.97. So of course, because it's sinusoidal data, like the actual fundamental relationship is not a constant, but again, these central tendencies don't care about the actual distribution, the underlying shape of the distribution. They care only about the central points where data tends to cluster. All right. So we look at this, and I'm going to put the plot here, and we see 4 artifacts. So these artifacts push the mean quite high up, and we see it here, 87. Which is about 7 millivolts higher than the reality. And you'll see again, that median kind of cuts directly through the center. Whereas the mean, well, it's up here. It's cutting maybe the top, 2/3 or even 4/5 of the actual waves, or the typical waves. But again, the reason this happens is because that artifact pushes it up. It adds all of these together, and then divides it by the number of data points, in this case 1,000. Whereas the median, it doesn't care about that. It looks at, okay, it basically orders these from the smallest, right, which would be around here, all of these values, it sorts it all out, and then it says, okay, I mean, obviously these are at the end. And with the sorted data, it's like, all right, well, what's this middle? And the middle is pretty much right here. Beautiful. So again, this is an interesting way to kind of decipher the data. It's not the only way to do this, as you could imagine. With when you have outliers like this, well, the mean can still be useful. You just have to, well, remove the outliers, especially when you have pretty high confidence that they don't belong there, that they're artifacts, that they're noise. So in my next video, I'm going to be going over the trim mean and other measures of central tendency, because what we're talking about here is the arithmetic mean. There's also the geometric mean, the harmonic mean, different forms of means to look at functions, central tendency, or random variables tendency. Anyways, so that's it for this video, and on to the next one.